Okay, excellent. So we're recording. Okay, so there are a couple of topics which we're going to be looking at in today's webinar. The first one is one which we've been doing in the actual sessions and in yesterday's both on campus and webinar session. But some of this may be sort of going over ground which I've gone over before, but it's best that we leave no stone unturned, and I don't mind. I don't mind repeating myself. It's best that it gets embedded. So stability. Essentially, stability is determining whether we can or cannot use a particular method to solve an ordinary differential equation. And this all stems from the fact that we're only ever approximating an ODE. With Runge-Kutta methods is we truncate our Taylor series. So let's say we want a fourth order solver, we would truncate all the terms of fifth order and above. And of course, so that's going to introduce some errors. So the errors it introduces, we're going to formally define them here. So a local truncation error, this is known as tau, and this is essentially what is the error from one step to the next. So if you are single step methods, we've got the current solution, we go forward a step to calculate the next solution. So over that step, there's going to be some errors due to our approximation, so that they're known as the local truncation errors. The global truncation error, this is an accumulation of the local truncation errors. So as you can see here in this equation, it's just a sum of all the local truncation errors. So if you hear me talk about local and global truncation errors, that's what I'm talking about. Now, stability is all about controlling these errors. So if these errors grow or are allowed to grow over each step, then eventually, after you've done enough steps, you're going to have your solutions going to be either plus infinity or minus infinity. Okay, because the errors will just accumulate. So we need those local truncation errors to always be bounded, but they're not growing from one step to the next. And so this is what we call in terms of stability. So if our local truncation error at a future step minus our local truncation error at the current step, if the absolute value of that is less than or equal to 1, it means our errors do not grow and we have a stable solution. Oh, righty. Everyone all right? Okay. So I'm going to just show you an example. Okay, so here I'm going to use Euler methods to solve a very simple first order ODE, y dash equals minus 2.3y over the domain 0 to 5 with some initial condition 1. Okay, this, because it's a simple ODE, we could have just calculated the solution by integration, and this ODE is the solution e to the minus 2.3t. So what this code does is it defines a function, it defines the exact solution, and it uses the Euler method to solve it. Now, with just a quick note on MATLAB, what I've got here is I've got a function called Euler, and if I zoom right to the bottom of the live script, you can see this is where I've defined it here. So you can define your own functions in MATLAB live scripts. The only problem is they have to be at the bottom of the page. Can be a bit of a pain. Okay. I'm getting a little bit of feedback. So has anybody got their mic on unmute or something like that? Yeah. Unless you want to ask a question, by the way, that's fine. So here we have the IVP. And what I'm going to do is I'm going to solve it using step length of 0.1. Now this is, I've just edited this code slightly from the one in the notes and the one which is on the live script on Moodle. So I just edited it slightly, but it's not too much difference. So here's the result. Okay, if I can just get them in the same. Yeah, so here's the result. So we can see it's using quite a small step length of 0.1, we have a solution. Now, we know that as we increase our step length, we're going to have a solution which isn't as accurate. So you can see I've increased the step length and we've got this big separation here between our numerical solution and our analytical solution. So if I increase it again, what we start to see Okay, so we start to see quite a big error. So you can see, let's take this point for example. Okay, so this is the exact solution. So here we have this. This is our global truncation error. Hit for that point, that's our global. So this is accumulation of errors at that point. But what you see is these errors are bounded, so they're not growing. So they're actually they're getting smaller as we go on. It's a poor approximation of the solution, but as it stands, this is what we call a stable solution. If I increase H slightly, you can see it's getting worse. Okay, but it's still stable. So these errors are still bounded. But if I go to 0.9, what you can see here is now our errors are growing. So when H was 0.8, we had a stable solution. It was a rubbish solution, but at least it was stable. But when H is 0.9, we have an unstable solution. If we were to continue along the domain, if we were to calculate, if we were to extend the domain a bit, so let's do that. Okay, you can see it's just going to disappear off after a few more iterations. We're going to get a useless solution. It's just going to go to infinity. So that's what we mean by stability. When could I ask you guys to put on mute unless you want to ask a question? I'm getting quite a bit of feedback, so I'm just going to. You're right. Yeah. Okay. Right. So that's the stable solution. Okay. So is everybody okay with the idea of stability, unstable, unstable? It's all to do with that step length H. Okay. So the way we examine the stability of a given method is we actually use what we call a test ODE. So this is lambda dash equals, y dash equals lambda y. So this is this here. Okay, first order ODE, it's also what we call an autonomous ODE in that it doesn't have the variable t there. Now, the reason we're using the test ODE is for simplicity. So it allows us to simplify our analysis. Now, what this means is from now on, unless we're solving the test ODE, we can't get a specific value for which H will remain stable. But what we can do is we can make comparisons between different methods to have a look at their stability properties. Okay, to look at stability properties, we look at the idea of a stability function. Okay, so when we're updating a solution over a single time step, so yn is our current time step, step in our domain. So yn is our current solution, yn plus 1 is our next step solution, and we're going to do something to our current step solution. And what we have here is we've got the definition RZ. Now RZ is the rate of growth over a single step in the solution. Now, if this is a rate of growth in the solution, it must follow, but the errors will also follow the same rate of growth. So RZ is how much errors grow from one step to the next. So if we have a look at the Euler method, okay, so this is the Euler method, should be familiar to you by now. Okay, so what we mean by this is our tau, our local truncation errors, also follow the same method. Okay, so I'm just notice there should be an F there. Okay, I don't know whether that's the same on your notes. I just put that in. Okay, so there should have been an F there. Well, for our test equation, f of ty or f of t tau is lambda tau or lambda y. So what we got there is h lambda n instead of f of t f of ty. Okay, if we let z equals h times lambda, then we have this. So what we're updating our yn plus 1 by multiplying our current solution by 1 plus z. So therefore, our stability function for the Euler method must be 1 plus z. So we want our errors to remain bounded. We don't want them to grow. So this is what we call absolute stability. And so the definition of absolute stability is that Rz is less than or equal to 1 for all z in the complex plane. Okay, and continuing on from absolute stability, we also have what's called the region of absolute stability, and this is all those values of z for which we have an absolute stable method. Okay, so what we can do is we can plot the region of absolute stability for all points in the complex plane. We're going to calculate what Rz is and then plot a contour line where Rz is equal to 0. Okay, so I'm going to show you how we do that here. So as always, clear the memory. We need to generate our z values. Okay, so I'm going to say that x is I'm going to say x is an array of real parts, and y is going to be my array of imaginary parts. So this linspace basically is going to generate 100 numbers between -5 and 5, which are equally spaced. Okay, then I'm going to use a mesh grid command. This will turn my my 1D arrays into 2D arrays, big X and big Y, and then I'm going to define my imaginary number. Okay, so Z, I've now got a 2D array Z of imaginary numbers. So now I need to define the stability function. So that's Rz. So I'm just going to call it R. And we saw up here that Rz was 1 plus Z. Okay, and now we just need to plot the region of absolute stability. Absolute stability. Okay, and I'm going to use a filled contour plot for that. So it's contour F, which is a filled contour plot. We're going to plot x against y, so x against y, and then we're going to plot the absolute value of R. Okay, this sort of 2-element array, essentially what this means is I'm going to have one contour line at where abs R is equal to 1. Okay, and I'm going to just increase the line width so it's 2, so it looks a bit thicker. Okay, so if I run that, you can see it's going to be a rather snazzy, background. Okay, so what I'm also going to do is I want to plot the real and imaginary number lines. So that's just a line which on the x-axis. So I'm just going to plot an imaginary line where x is equal to 0, and it's going to be a black line, and I'm going to plot another line where x is equal to 1. Sorry, x equals 0, but y goes from -5 to 5. This just sort of, it's helpful just to see the real and imaginary lines. Okay, I've got a rather snazzy color scheme, but I'll leave that color scheme as it is. Okay, I'm going to zoom in a little bit with the axis command. So let's zoom in slightly by changing our axes. Okay, so what we have here is we have this region, which is a circular region. Okay, everything inside this circular region means the Euler method is stable for our test equation. Okay, so any z within here, remember z is equal to h times lambda. So any z within this region is stable. Anything outside is unstable. Can't quite know why I've got a snazzy color scheme on that one, but we'll leave it for now. Okay, so these plots are useful. So these are plots of absolute stability. They're useful for actually comparing stability properties of different methods. Right. So we could also use them to determine the interval of absolute stability, which is just a range of real values that step length of a method can take to ensure that it's stable. So if we look at our plot, so this is the real number line, so that's our interval of absolute stability with the Euler method. So it's from -2 to 0. Remember, this is z, so these are z values. So if for our Euler method, our interval is -2 to 0, and z is h lambda, so h must be in the range -2 over lambda to 0. So therefore h must be less than or equal to -2 over lambda. So our ODE, which we solved in the original, in example 4.1, was y dash equals -2.3y. So therefore, in this case, lambda was -2.3. And if we use this, we can see that the maximum value of h for which our method would be stable would be 0.8696. Okay, so that's why between 0.8 and 0.9 we had a stable and an unstable solution. Right, so that's the whole idea of absolute stability and stability. Obviously, we're looking at Runge-Kutta methods, and we've got two types. We've got explicit and implicit. So we need to determine stability functions for both of those types. So just to remind ourselves, this is a general form of a Runge-Kutta method. And when we looked at implicit methods, we used this simplification. So remember, we introduced a big Y so instead of the second argument in our function in the stage value, we're going to use this. And because we're using a test ODE, so f of ty is just lambda y, this simplifies our Runge-Kutta method to these two. So this is the updating of our solution, and this 4.2, equation 4.2, is the stage values. So you can see it's actually simplified it quite a lot. We don't have a function, and notice that our coefficient lambda comes outside of the summation. So if we expand out the stage values, which is 4.2, okay, so if we have s stages, all I've got here is just expanded out each row of this summation here, and we're going to introduce vectors. So if big Y is our vectors of stage values, big Y1, big Y2, etc. E is just a vector of ones. We can write all of this system as this vector equation here. Okay, so the E, 1, 1, 1, etc. That's E times Yn gives us all of these Yns here. Then we've got Z, and you can see, but everything in the brackets, all of these summations is simply matrix multiplication of A times Y. And also we can use matrix multiplication in equation 4.1. Okay, so instead of this summation, we have the B transpose times Y. And I mentioned this before, but we always assume that B is a column vector. Okay, so we're going to be dealing from now on with the vector form of the Runge-Kutta methods. So for an explicit method, if we rearrange 4.3, we get this. Okay, so we got this will be a matrix, so this is an inverse of a matrix. And we substitute this into 4.4. Okay, we have this. Okay, so therefore our RZ must be this expression here. But the problem is this expression has a matrix inverse, but fortunately we can approximate that inverse using what's called the geometric series of matrices. So this is an infinite series, okay, which is the approximation of this matrix here. Okay, so this leads us on to equation 4.5. And we have our stability function. Okay, so it's a polynomial function, 1 plus something times z plus something else times z squared, etc. Now, we've already seen that the solution to that test ODE was e to the lambda t. So what we want is our errors to follow the same or to grow in the same rate. So this is the series expansion of e to z. E to the z, as you can see, it's just the nth term is 1 over n factorial times z to the power n. And if we equate 4.5 and 4.6, you see that we have this condition. You might have this was actually one of the order conditions for implicit Runge-Kutta methods. So you have kind of seen this or something similar to this before. Okay, so this must be satisfied up to the kth term for an order k method to be stable. Okay, so let's have a look at this. So here we're presented with example 4.5. So we've got an explicit Runge-Kutta method. So I'm just going to define it in this code cell. Okay, so we have our A matrix. Now we have four stages. Okay, so we're going to have 4 rows and 4 columns. Okay, I'm not doing this very neatly, but do it quickly. Okay, so that's our A matrix, and we also need our B vector, which remember we assume it's a column vector in all of our work. Okay, so that's all we need. We just need A and B. We also need that vector E, which is going to be a 4x1 array of ones. So just show you what that ones command gives us a 4x1 array of ones. Okay, so now we can calculate the coefficients of z, or whatever z to the k is. Okay, so the general form is whatever k is, it's b transpose times k a to the k minus 1 e. So when k is 1, we just got b transpose times e. When k is 2, we got b transpose times a times e. When k is 3, we got b transpose times a squared times e, etc. Keep going. It doesn't matter how long you go do these for, it'll eventually you'll get a value of 0. So I'm going to run this in a second. So if I've done a few there, if I run that, okay, you can see we have some answers. It's often useful to actually use the rat command on each of these to get the fraction. Very quickly, just do the rat command. Okay, so you can see we have these coefficients. So our stability function for this method was 1 plus z plus a half z squared plus 3 over 16 z cubed, etc. So that agrees to this this series expansion 4.6 up to the second order term. Okay, so so that means this is a second order ERK method. Okay, even though it had 4 stages. So you're doing sort of 4 function evaluations to calculate a single step. It's only second order. So to be honest, this is quite an inefficient method. Okay, so what we're going to do here is calculate the stability functions of orders 1, 2, 3, and 4 explicit Runge-Kutta methods. And rather than watch me again type out a load of MATLAB code, I'm going to copy and paste in from what I have done previously. Okay, so this is given in the notes as well. So okay, so it started off the same as what we did for the Euler method. So generate your z values, define the stability function. So remember, this is just the e to the z series expansion. So what you'll notice is, for example, the stability function for the 4th order method is the stability function for the 3rd order method plus that 4th order term there. Okay, so let's just run that and see what we get. Okay, so here we have 4 regions of absolute stability for the ERK methods up to the 4th order. So the blue one here was the Euler method. The red one is 2nd order. Black one is 3rd order, and sort of the magenta one or the pinky type one is 4th order. So you can see actually as you get the 3rd order methods got a larger region of absolute stability than the 1st and 2nd order, and the 4th order's got a larger still. Okay, so those are your stability regions for the explicit methods. Okay, on to implicit methods. If we look at the simplest implicit methods, it's one called the backwards Euler method. So we have this implicit equation here. So we've got yn plus 1 on the left, and we've also got yn plus 1 on the right. So it's implicit. If we factorize and solve for yn plus 1, we have our stability function is 1 over 1 minus h lambda, or, because since z is equal to h lambda, 1 over 1 minus z. So this shows that stability function for implicit methods take the form of a rational fraction. So the stability method is some polynomial p over another polynomial q. Okay. If we want to plot the stability region of absolute stability for the backwards Euler method, which again I'm going to copy some code in, which I've already done. Well, actually, I could have copied it in from the previous work. Okay, so you can see the only change from the first example on this live script is where we have a different stability function. So if I run that. Still think about it. Here we go. Right. So this is the region of absolute stability for the backward Euler method. Okay. Now it's quite similar to the to the normal Euler method, except the region of stability is outside of this circle. So the shaded region is outside. So within this circle, the backward Euler method is unstable. Outside of the circle, it's stable. Okay. So therefore, we've got much greater range of values which h can take, for which this backward Euler method is stable. So that sort of reinforces the main sort of the benefits of implicit Runge-Kutta methods. We've seen last week that they're harder to apply, they take more effort, but they're much better stability properties. So if you have a look at the stability for an implicit method, okay, again, we're going to be using the vector form of our Runge-Kutta method. Remember, this is the vector form when applied to the test equation, that test ODE. So transposing these equations, but the known values of our solution is on the right-hand side. And so in other words, the terms not involving yn are on the left and yn is on the right. We can rewrite this as a matrix equation. So the first row is the first equation. Okay, so you can see it's yn plus 1 minus 2 times b1 times y1 minus 2 times b2 times y2, etc. So that first equation is given by the first row. And all the others here are given by this submatrix down here. So 1 minus ZA, Y1, 1, etc. So all of these, this submatrix here is I minus ZA multiplied by Y, and that gives the E to the YN there. Okay, so if we had big N stages, or sorry, if we had S stages, this is an S plus 1 by S plus 1 coefficient matrix. Now we can solve for the first yn plus 1. We can solve for that first unknown there using Cramer's rule. So thinking back to your first year, Cramer's rule, we replace the first column of the coefficient matrix by the constant vector. So you can see what all the yns there. And it's the determinant of that divided by the determinant of the coefficient matrix. Now, if we, so the numerator is just a straightforward, well, I'd say straightforward, it's just that determinant. If we expand down the first column to calculate the determinant of the coefficient, okay, you can see because all of these are 0, it's just going to be 1 times the coefficient of that submatrix. And that submatrix is I minus ZA. Okay, so we can rewrite yn plus 1 using this. Okay, and if we perform a single row operation by subtracting all rows below the first row, oh sorry, if we subtract row 1 from all rows below it, we get this. Okay, now the stability function for an implicit Runge-Kutta method, so we can simplify that to give us this. Okay, so we have determinant of I minus Z multiplied by A minus EBT. So E is that vector of 1s and B transpose is a row vector of B's. Okay, and also EBT is a diagonal matrix, so it's the same size as A, but elements would be on the main diagonal. Okay. So that's our stability function for our implicit method. And we've spoken about how implicit methods got much greater interval of absolute stability than explicit methods. Some implicit methods have got another, they can be referred to as astable. Now, astable methods are really useful because there's no limit on the value of h for which we can, for which a method is stable. So it'll be useful to know which or whether you have an implicit method which is astable. Okay, so the definition of astability, okay, is, or the region of absolute, a method is said to be astable if its region of absolute stability satisfies this. That means for all z in the left-hand complex plane, so that's where it has negative real parts, so anything to the left of the origin, if the value of our stability function is less than or equal to 1. Okay, now how we can tell whether something is astable or whether a method's astable if we have our stability function in this form, so Rz equals P over Q. So Pz is a polynomial and Qz is another polynomial. We define this function Ey. Okay, and a method is astable if the roots of the denominator of our Rz are positive real parts, and if Ey is greater than or equal to 0 for any y in our real number range. Okay, so here we've got an example 4.8, which I've written out in full. I say in full, I've done it without using MATLAB. Okay, so here's implicit Runge-Kutta method. It's two-stage. So I've got to use equation 4.7, which is 4.7, just to remind us, it's this one here. Right, so I've got I minus Z, that's our A matrix, and this is that EBT matrix. So if we've got B1 is 3/4 and B2 is 1/4. Okay, because this is a 2x2, it's not too tricky to actually calculate the determinant of. Okay, so we've got that there. Okay, so determinant, and eventually we get down to this. Okay, so this is our Rz, and notice it's a polynomial function on the top and a polynomial function on the bottom. So the first criteria was, are the roots of Qz, are they in the right hand side of the complex plane? And if we use the quadratic formula on this, we get the roots being 2 plus or minus root 2i. We're only interested in the real number part, which is 2, which is positive. So that's the first condition. For the second condition, if we determine what Ey is, okay, this does require a bit of algebra. And when you do this, you should find that the imaginary parts do cancel out. Okay, so we're left with 1/8 y squared plus 55 over 2304 times y to the power 4. Now, both of these have even powers. So if y was negative, these would still be positive. Okay, so either y is greater than or equal or greater than 0 for all y in our real number line. So the second condition is satisfied. Okay, so we can say that this method is astable. And this method in particular is actually a really useful implicit Runge-Kutta method. Okay, so I'm going to plot the region of absolute stability for that method now. So this is using a very similar code to before. So actually, if I just, so remember what I said, well, I've said over the last couple of weeks, there's no point redoing something we've already done plenty of times before. So if I copy and paste that code in here, and the line I need to change is, if I can get them both on, I need to change our stability function. So on the top, we had 1/3 times z plus 1/16 times z squared. Notice I've used a dot power because we want element by element, and I also have to use a dot divide. So usually MATLAB will throw up an error if you haven't done this. So 2/3 times z plus 1/6 times z fast squared. Okay, so that's this function put in here. Okay, I might have to mess about a little bit with the range. Okay. Oh yeah, you can see it's sort of too far zoomed in. So if I zoom out a bit by changing our axes, so let's go from -5 to 5. Bit of trial and error here. You know, you might not get it straight away. Oh, I need to go about a bit further. So let's go from -10 to 10. Okay. Like I say, a bit of trial and error is always expected. I also need to change my x and y values. That's a sort of general thing on MATLAB. Actually, don't always expect you to get things right straight away. It does take a while to do these things. There we go. Okay, so this is the region of absolute stability. I'll say of an IRK method, just to be correct. All right, so that's the region of absolute stability. So remember the shaded region, the blue region, that's where we're stable. So you can see here, our interval is everything in this will extend to -infinity. It's everything in the left-hand plane. So we're always, so whatever value of h, we're always stable when using an astable method. Okay, so that's stability functions for implicit methods and explicit methods, and also how to plot the region of absolute stability and the idea of astability. So there are a couple of questions in the assessment, the coursework assessment, which you can now be able to answer. Okay. One thing I also want to mention, I know Lida will be covering this as well in her part, the idea of stiffness. So stiffness, essentially, it's a way, or it's a term we give to any problem which is awkward to solve, so to speak. So quite often, especially in practical problems, well, you'll have a system of ODEs which has a really stringent stability constraints. And this is the idea of stiffness. Now, there's no sort of hard and fast mathematical definition of stiffness. But the one which I like is given in Lambert is if a numerical method is forced to use in a certain interval of integration a step length which is successfully small in relation to the smoothness of the exact solution in that interval, then the problem is said to be stiff in that interval. So this means if the problem, let's say you're applying your ODE solvers to a problem and you're getting an unstable solution, or your method is unstable, and you keep reducing and reducing the step length h, and it's still unstable, that's probably an indication that what you're trying to solve, the ODE you're trying to solve, is stiff. Okay, this is why astable methods are really useful, because astable methods can solve stiff problems, but non-astable methods would struggle. And similar to multi-step method, you've got an implicit multi-step method. They're really good for solving stiff systems. We can actually sort of give an indication of whether a system is likely to be stiff or not. Let's say we have a linear system of equations. So y dash equals ay, so a is some coefficient matrix. So if we could have, let's say, 10 ODEs. So we'd have a 10 by 10 A matrix. When we're looking at a single, the stability of a single equation, we use the test ODE, y dash equals lambda y. So we need to transform each of our individual equations into that form. So we're going to introduce ui, which is some transformation of yi. Okay, and I'm going to say that ui dash is equal to lambda I ui. Okay, so similar to the test ODE. Furthermore, lambda I are eigenvalues of A. Okay, so we can write our system of transformed equations as u dash equals big lambda u. So this looks like an A without the horizontal bar It looks like a capital A without a horizontal bar. This is actually the uppercase Greek character lambda. Okay, so what this means is lambda is a diagonal matrix with eigenvalues on the main diagonal, as you can see there. So we need to show that we can have a linear transformation from Y to U. Okay, so if we let V be a matrix containing all the eigenvalues, eigenvectors of A, corresponding to each eigenvalue lambda I of A. So in other words, if we multiply A by V, we have this. Now, since by the definition of an eigenvector and eigenvalue, AV is equal to lambda V, what we have, excuse me, is V times our matrix lambda, or big lambda there. Okay, if I inverse V and pre-multiply both sides, we see that V inverse times A times V is equal to diagonal matrix lambda. Now, back in the first year, you looked at linear transformations, and you proved back in the first year that an inverse times a matrix, an inverse matrix times A times the matrix V again was a linear transformation. So we proved that we can have a linear transformation from our test ODE to UI dash equals lambda I UI. Okay, so that means we can assess the stability of our original system by looking at the stability of U dash equals lambda U. Now that's important because A might not have been a diagonal matrix, but big lambda is a diagonal matrix. Okay, now a stiff system will have a large variation in the step length. So for some equations, you might have a large step length permitted, and in other equations, you might have a really, really small step length. Now that's all based upon that lambda value. So remember you got Z equals H times lambda. Well, that's going to be dependent upon that lambda value. So what we do is we have what's called a stiffness ratio. So in other words, it's the maximum eigenvalue of A. So remember, A is our coefficient matrix divided by the minimum eigenvalue of A. And that gives us what's called a stiffness ratio. And if that's large, it means you've got a stiff system. If that's small, you've got an unstiff, well, unstiff, you haven't got a stiff system. What is considered large is there's no real hard and fast rule. It's just a general guide. So for example, an S of 1,000 could be stiff, maybe S of over 100 might be stiff. And it's kind of a guide. It's not really a hard and fast sort of definition. So if you look at an example, so let's say we wanted to solve this second order ODE. Okay, so we can split it up. We can write it as a matrix equation and calculate its eigenvalues. So in this case, it's 1 and 1,000. So we have a stiffness ratio of 1,000, and that ODE can be considered stiff. Okay, so that was the first part of what I wanted to look at today, stability. So just to summarize, local truncation errors is the error at each step of a method, and global truncation error is the accumulation of those local truncation errors. A method is absolutely stable if the local truncation errors do not increase from one step to the next. We use the test ODE, y dash equals lambda y, to analyze the stability. So I'll stress this again, but it's quite tricky to actually find a maximum value for H for which a method is stable for any sort of generic ODE, because that will require a lot of analysis, a lot of algebra. So what we do is we just tend to use this test ODE to compare different ODE solvers. Okay, you can tell whether it's unstable if you just try and calculate it, and you'll notice the solution disappearing off to infinity. The stability function of a method is the amount by which the solution to the test ODE changes over a single step length. And the region of absolute stability are all those values of Z in the complex plane for which the modulus of the stability function is less than or equal to 1. Showed you so how to determine stability functions in equation 4.5 and 4.7. Okay, the explicit Runge-Kutta method should agree to the series expansion of e to the z up to the kth order term. So an order k method should agree up to the kth order term. Implicit methods can be astable, which is really a property which you want, because that means there's no limit placed on the value of the step length. But I should also sort of caveat that with there's still accuracy concerns as well. So you might have an astable method, you might choose a large step length, and your local truncation errors aren't increasing over each step, but they're not increasing, but they still might be quite large because you're using a large step length. So just because the method is stable doesn't mean you should use a large step length. And finally, a system is considered stiff if the ratios of eigenvalues of the coefficient matrix is large. And stiff systems require methods that have larger regions of absolute stability or astable methods. Right, okay, so that's kind of stability. That was the first part I wanted to cover in today's webinar. Okay, I'm just going to stop the recording there. Hopefully it has worked. Fingers crossed.